I am Bill Venners, and this is Frank Sommers, and I wanted to clarify that Frank is actually not part of the title of the talk. He's a co-presenter.
It's just, unfortunately, bye-bye. I think we can talk about it.
The reason that we're here together is because we are working on a book called Effective Scala, and we have not really started, but that's our plan. And
but it's in the works.
We have created a workshop and this talk. So this talk is just, we wanted to talk about one idea.
And I think the other reason we're here is because we have been working with Scala for a really long time, and probably everyone knows Bill, because Bill is the author of the Scala test framework, which has been around for a very long time. And we started about the same time working with Scala, I would say about 2008 or so. And so what I've done since then is to go on and start a company that actually uses Scala in an enterprise software setting. So we have a little different sort of takes on the effectiveness of using Scala, and I think that that's what we're trying to talk about. And so as a starting point, I'd like to say that those who were at Martin's keynote 2 days ago may remember that Martin mentioned that Scala is really more than a language. It's really a language toolkit. So the language, even though the language nudges you in certain directions of programming style, it really doesn't enforce a particular way. And that's a great thing in many ways. It gives you great flexibility, but it also gives you a really wide latitude. And so when you have a code base, such as ours, for example, is probably a 9-year-old code base. And again, it's in production. It's used by different companies. It could be a problem if the styles in the code base really diverge. So in this talk, we will try to give you a few guidelines and a few pointers in terms of how to mitigate this really wide latitude that Scala offers. And it's based on our experience. So on one end of the spectrum, you could program in Scala as if you were programming in Haskell. And I think the term Martin used is a worse Haskell on the JVM. And I think he even made a point, if I correctly remember, that Scala may not, even though you can actually do Haskell-like FP on the JVM with Scala, but Scala may not necessarily be the best basis for that sort of pure FP approach on the VM. However, it's possible. You can actually do that. At the other end of the spectrum are mostly those who come to Scala for the first time, typically from Java. And you can obviously write Scala code as if you were writing Java code without the semicolons. So you have these two extremes. And what we try to say here today, and even convince you, hopefully, is that there is a third way, which we think is really represents the sweet spot for Scala. And so that's where our effective Scala guidelines will come. And we'll give you 3 guidelines in this talk. And hopefully, if you apply to these guidelines, especially to new Scala projects, hopefully they'll prove to be beneficial.
Yeah, and each of these are quoted because I heard Martin Odersky say each one of these 3 things. He said the first 2 in his keynote yesterday, and the third one I heard him say it in a advisory board meeting. And what we're really trying to do is flesh out what does that mean? What is this third way that is the sort of the idiomatic way to use Scala? So we do think that this third way is probably the best way for most projects. What Better Java, as Frank mentioned, is I think really good for is if you're just starting out in Scala and you're coming from some imperative language like Java, it's fine to just program in the way you know and get things done. And over time, you'll learn more idiomatic ways to do things in Scala, more functional ways. And I have seen the Haskell on the JVM way work also in practice in actual companies doing that. But what was always the situation is there was a leader on top who knew what parts of that they think made sense, and they made sure everybody on the team understood what these concepts are and were kind of going in the same direction, and they maintained consistency across the project. What I have seen many times is that most people on a project will be doing this sort of idiomatic Scala functional but not Haskell way of writing code. And then there's a few people who are passionate about Haskell off to the side doing more that direction, and then the rest of the team can't understand the code. So one of the things we think is important is that management, like when you're managing the project, that you kind of make sure that you watch the consistency. Because Scala is unopinionated, the code base can be all over the place. And it's great that the community is all over the place. That's very interesting, and that's one of the things that makes our community great. But in a specific project, it's good to have kind of one style that the whole team is following.
Yeah, and that segues into our first guideline, which basically is very simple. When you start a Scala project, it's pretty important to pick an opinion, form an opinion about how you want things to look like in your code base. And you're free to pick whatever opinion you like. If you like to do the FP approach, that's great. If you like to do the more Java-like imperative approach, maybe that's okay too. I think Scala lets you do that. But in my experience, what is important is to pick one opinion or what point of view and stick with that throughout the project, at least as long as you can, because it will keep your code base consistent relatively across time and also across teams. So when new team members join your project, they will be able to adhere and follow that style, even though they may not necessarily like it, but they would follow it. And I think that's quite a good way to work with a Scala code base over years and teams and time.
Right. So Scala as a language is unopinionated, but your project should be opinionated, essentially. So we wanted to give you an example of a way where I think Scala as a language, maybe not so much the library, but as the language itself, it's very unopinionated, but that I think most of us would agree we are more opinionated. So, and that is that this comes from Jamie Allen. He called it the mutability matrix of pain. And I thought that was a little negative. It's not really good marketing for Scala, so I rebranded it the immutability matrix of pleasure. But essentially, Scala gives you these 4 choices. There's 2 kinds of variables, vals and vars. Vals are, you can initialize them, but you can't change what they refer to. Vars, you can keep reassigning them so they can refer to a different object over time. And immutable objects can't be changed after they're initialized. The contents can't. But mutable objects can change state over time, so they're much more interesting. But you can have a val refer to a mutable. You can have a val refer to an immutable. You can have basically any combination of these 4. So what do you think would be, I'm just going to let you think in your head so you don't embarrass yourself and vote for the wrong one. Which one do you think is the happiest quadrant? So just pick one. And then, Frank, what do you think?
Well, which one is the most boring is also the happiest, because I think in that quadrant there, like it's basically a pure immutability. Nothing happens. It's an immutable data structure, and a val points to this data structure. So what that does give you, though, is the ability to reason about your code. So this is a perfect example where the FP approach truly shines. If you can stay in that quadrant, then I think you'll be happy over time. And
so what is number 2? So that's number 1. What do you think? You can just think in your head. What do you think is number 2? This is a little trickier. So we're gonna choose one, and it is this one. So this is not quite as happy, and the reason we picked that as number 2 is because it's easy to close over objects and send them somewhere else. And if it's a mutable object and you send it somewhere else where there's multiple threads hitting it, then you've just got a concurrency bug in your program. So it's just a little bit safer to have immutable objects in memory that you're holding to from vars, and you're replacing them, reassigning the var to point to a different immutable object. Okay.
I think the next one is a pretty easy one. I don't think we're going to have to take a poll. But this is the next quadrant. So if you cannot stay in one or the other, then this would be the 3rd place to be at, possibly. So why would you want to do this? Well, most of the time you would do this for performance. And the fact is that some algorithms are just basically faster to implement with a mutable data structure. I will show you many examples of that. But this would be the 3rd place to stay. So it's a val. It's pointing to a mutable data structure. And again, Scala lets you do that. It's just a very simple thing in Scala to do.
And then the last one is interesting because in Scala, I don't know that I've ever used that, and I don't know if I've ever seen that, and I just don't think that combo is necessary. And I think 2 and 3 are pretty close to each other. So those guys are actually pretty close to each other. But the 4th one is just not really useful in Scala. But what's interesting about it, I think it illustrates 2 things. One is that Scala does have an opinion, not the language per se, because in the language it's just as easy to say val something equals mutable immutable var something equals mutable immutable. It doesn't really guide you in one direction or another. But Java does. Java says that the lower right-hand corner is the normal way of doing things. And normal variables are not final, right? They're like a var. Normal objects are mutable. So like Java, C++, C#, Ruby, Python, all these languages that sort of were mainstream languages preceding Scala have a different attitude. And so Scala is trying to suggests there's a better way to program. The other thing it illustrates, I think, is just that the language is unopinionated, but we should be opinionated. So.
So I think the takeaway from this is that when you approach a code or you have code reviews, it's good to pick one approach that you like to take, and maybe it could be that left top quadrant, or whatever quadrant, but regardless, you should think about this. It's very important. And so our second guideline is that Scala, of course, gives you lots of FP and lots of OO tools in its tool set that will all let you manage complexity, especially as your code base grows. So it's really important to know which particular parts of FP and which particular parts of OO will help you solve your problem.
I just realized we didn't define that. FP is functional programming.
Yeah.
Probably most everyone knows that, but just in case. OOP is object-oriented programming. So that is like, Scala is a blend of those two things. That's the point of it.
So this is probably our second guideline, just to think about it consciously before you start a project, and then make decisions about which parts to use in your project.
Right, so what we want to do is show you some specific ways that FP and OOP help you manage complexity. So and this is as code bases grow large, not when it's small, right? So the main way that FP helps you manage complexity is that FP is, encourages pure functions. A pure function is something that just takes its input and does some number crunching or whatever and returns a result without having any other effect off to the side that isn't sort of embodied in that result. And referential transparency is what you get when you have pure functions. Referential transparency means that I can take an invocation of a function where you pass in particular data and just replace that whole thing with the result, because every time you pass the same input to a pure function, it will always give you the same result, so it doesn't matter where you call it again. You can just plug in the replacement. And what that actually lets you do is it's composable. What that gives you is composability. And you can compose more pure functions out of existing pure functions, and then create other pure functions out of that. And you can have this big tree of function calls, but at the top, it's still pure. You pass in maybe a big complicated data structure, and you get back maybe a big complicated data structure, because it's doing a lot of stuff, but there's nothing else off to the side that you have to keep track of. So we want to give you some examples of where that's always been the claim. We want to give you some examples of where that sort of support that theory, that helps you reason about code. But we wanted to first say that it actually it doesn't mean that you can't reason about imperative code or impure code, because you can in the small. So in the small, it's perfectly easy to reason about imperative code or impure code. And so an example that we have here on the screen is this is how lists exists method is implemented. It's got a var, it's got a while loop. It reassigns the var in the middle of it, but it's small enough that you can look at that and figure it out. You can understand it. And it also doesn't return a mutable object. It returns an immutable object, which in this case is a Boolean. So from the outside, it appears, it is pure. It always returns the same result given the same input. So you still have the benefit of referential transparency on the outside, and on the inside, it's small enough that you can understand it.
Yeah, but that doesn't really hold, of course, when you program in large. So this is an interesting example. Most people think that garbage collection, of course, is a wonderful thing, which it actually is. But I think that Bill was mentioning this to me a few years ago, that if you guys remember programming in C back in the days.
They're probably too young. But,
well, we don't know. I think a lot of people still
revealed a little bit of our age.
C.
You remember.
There we go. So in C, basically what you had to worry the most about really is managing memory, managing the heap. So you can think about that as a large-scale problem of mutable state. If you think of the heap as a mutable state, basically, then without automatic garbage collection, it's really the programmer's job to manage how that heap is used. And so, if you make a mistake, there is going to be a big issue there, a big problem. The program will probably crash eventually, or immediately. So here, it's an example. Here you would allocate 4 bytes of memory, for example, on a heap. And then in the next step, you may allocate another 2 bytes and another 3 bytes. And then afterwards, you free 2 bytes. And so now, somehow or other, you have to keep track of the mutation of the state. And, there are various tools of doing this, but this is a big problem. And so I think this is perhaps an interesting illustration of how it's difficult, even though mutable state in the small is actually kind of okay, But in the large, it is very, very error prone. So
Yeah.
this is one reason that the industry actually adopted automatic garbage collection.
Even this example, I think you could remember that we already released P2, right? And that you won't release it again. But so in small examples, you can get it right. But what the insight I had, like many years later, after spending a lot of time struggling with memory errors in C, is that the reason it was hard to get this right is because that's a mutable data structure, and the side effects, you're mutating each time you malloc and free, and you just have to remember. You have to keep track of those side effects in your head. So another example that I think illustrates this problem of in the large, how it's hard to reason about side effects is synchronized access to shared mutable state. We all kind of probably agree that's hard to do. And the reason is another insight I had after I had realized and had experience that this was hard to do, is that this thing is a mutable data structure. So this is the Java's monitor that's associated logically with every object. And if you hit a synchronized method, if a thread hits a synchronized method, then this data structure will come into being. And what each of these circles is a thread, right? So if a thread is executing along and it hits a synchronized method, what it does is it enters the entry set of the monitor, which is like an entry room. It comes in the left side, and that is a mutation of this data structure, of this mutable data structure. And then if there's nobody in the middle room is special, it can only have one thread in it, then it moves in and acquires the lock, right? And so now it owns the monitor. That was a mutation. Right, that's the second mutation. If it returns or exits with an exception, either way, it will go down out the bottom and it releases a lock at that point. That's a mutation. And at that point, other threads may compete to get in there. If somebody calls .wait on the inside, that goes over to this back room, which is the wait set. And there's two kind of subcategories over there. You can be waiting to be notified. And once someone comes in here and calls notify, you go from orange to green. That's a mutation. When this blue guy exits, the greens and the yellows will compete to get in. When one of them gets in, that's a mutation, right? So it's mutation, 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 and it's all over your code. And it's just really hard. And in a small example, you can get it right. But in a big one, it's very difficult because side effects are hard to reason about.
And things can get large pretty fast.
Yeah.
So I think that, again, in the small, but what works in the small doesn't necessarily scale up in the large.
Except for referential transparency.
Except for referential transparency. So that's what makes really FP really so wonderful in Scala, that you can manage this type of complexity as your program grows. So do use those techniques. It really helps you do that. However, object-oriented programming also for many decades was also aiming at solving complexity of your code and your problems. So it would not be very nice to just throw out those features of Scala. Rather, we should think of what aspects of OO help you manage complexity. Clearly, not all aspects of object-oriented programming would be helpful for Scala programs or even effective, because they may just not fit with this FP approach at the same time. But many things do. So for instance, object-oriented programming often puts data close, the operations on the data close to where the data is defined at. And when you do object-oriented analysis of a large problem like a business domain, you often use class names and method names that are naturally expressing that domain. And whereas FP gives you a lot of understandability or reasonability of the code, object-oriented programming, and especially if it's done well, gives you accessibility of your code base. Because if a developer comes and looks at your code working on a certain domain, those classes and those, especially if it's again well designed, will give that developer easy access to what the code does. It expresses your domain. So that is one benefit of OOP that you could definitely use in Scala.
And
this is an example of a piece of code that even if you've never seen this, you instantly can use this code. You know what it does. It's obviously a class of a map. And you see there the nouns, which are essentially class names, express the domain. So you have latitude, longitude, you have a street view, panorama, and so forth. You don't have to dwell into the code in great detail. Like if you have a team, for example, if somebody were to work with this code, pretty much instantly this person will be able to use it. This actually happens to be a Scala.js facade over the Google Maps API. But this is just an example of something that's extremely natural in OO. You have methods on an object and the data. Now, I also have to mention, though, that state inside an object doesn't mean mutable state in object-oriented programming. In fact, especially this is an interesting example because in user interfaces nowadays, the trend is to get rid of mutable state in the user interface. However, if you program in React, that's an example of what they're trying to do there, which is a really, really good approach. But so state inside an object is a good thing, most likely, in many cases, but mutable state may or may not be a good thing. And
yeah, and sorry.
Yeah, go ahead.
Finish your thoughts, Senator. Okay.
All right.
I was just going to say that pure functional programs that just have data structures and functions, they have names, and they can be nouns and verbs. What we're trying to say here is that when you bring these two together and you make a class that combines nouns, state, the data structure with the methods, that actually helps people think about their code. And when it maps to the domain, like Street View Panorama, you could already guess what that probably means. So that's our claim there. And then the
now,
mutable state.
If you do have to have mutable state, then it turns out that encapsulation is really one of the main tenets of object-oriented programming, right? So even if you do have to deal with mutable state, then it turns out that objects actually are a pretty good way of doing that. You can encapsulate state inside an object, and you can define an interface to that object in such a way that when you mutate the state, that is quite well defined and it's understandable. So again, it's a good tool in object-oriented programming to encapsulate state and objects. We shouldn't frown on that.
The alternative is global mutable state. And so global mutable state, if that gets corrupted, it could be anywhere in your entire code base that caused it. Whereas encapsulation does is if the only behavior that can touch that mutable state is the functions on that, the member functions or the methods on that class, then that really narrows the problem. So it is, if you want mutable state, OO is a great way to deal with it.
And sometimes mutable state is useful. We should admit that, even though some people may like to say that we should not have any mutable state, but sometimes
I think that's what Scala says. And
that's what
so
we think that's what Scala says.
So here's an example. We wanted to give you an example of where we think it is useful to use mutable state. And that is for sometimes a mutable algorithm is the fastest. So an example is string concatenation. There's a make string method on list. And it's implemented this way. They create a string builder. What a make string has to do, it gets a start string, a separator, and an end string. And what it's supposed to do is return a string that starts with the start string, ends with the end string, and then has the two string of each element in the list separated by sep. Right? That's what it's supposed to do. So you could do that functionally by just concatenating strings. And each time you do one of those processes, you create a new string and throw away the old one. But it's more efficient to use string builder, and everybody always does that because it's faster. And so what this guy does is it actually uses another method on list called add string, which takes a string builder that could be non-empty, but in this case we create a new one here and pass it down. We pass in the 3 parameters to our method. And then we get the same string builder back. It's just mutated it. And at that point, before we return it, change it to an immutable. So from the outside, make string is pure. Basically, you call make string on the same immutable list, you'll always get the same result. Passing in the same start, sep, and end, right? And what I wanted to demo is, or just point out, is that B, when we pass in the string builder, B is a val, because parameters to methods cannot be reassigned. So this is an example of the third quadrant, where a val is referring to a mutable object, and the reason is because it's fast, right? So that is Scala's, basically enables that if where it makes sense to use mutation, you can do it.
And that brings us to our final guideline for this presentation today, which kind of brings this all together, I think. And that is that you should, in general, try to put side effects on the outside of your program and possibly also on the inside, the core of your program, like in this, for example, you just saw. And everything else, in general, you should try to keep pure.
Okay.
So what does that mean? It means that the outside of your program, well, what makes your program often useful is that it interacts with the outside world. So what does the outside world mean? It means, for example, I/O. You have to do I/O. If your program doesn't take any I/O, then, well, it can heat up the CPU. But even that one is actually a kind of I/O, possibly, I would think. But also, you might want to interact with this ton and millions of Java APIs out there.
Or JavaScript.
Or JavaScript APIs nowadays, like you saw in the Google Maps. And what that means is that those APIs will do whatever they want. They will not follow functional programming principles. They probably use imperative styles. They will have nulls all over the place. When you look at the facade for JavaScript API, well, let's see, even types might be questionable. You could have any, pretty much anywhere or everywhere. We would call this, so where you interact with this outside world, we would like you to think of that part of your code as the wilderness. Basically, anything goes in that part of your code. And we would like you to confine that wilderness to a well-defined region of your code. Now, inside of your code, like you saw in that string builder, you could also use imperative styles, like even the Scala APIs do that for performance reasons. The other reason you may want to do that is to use an existing Java API. There are just a ton of APIs that you may want to use. But what's important is to confine the use of these imperative APIs in such a way that from the outside, they actually adhere to referential transparency. So again, that's the core of these methods. And also, they are confined to one thread of execution. Because that way, you don't have to worry about concurrency. You could do pretty much what you want inside a little core of your program. And again, you would do this mainly for performance. And you might also want to do that, like I mentioned, to use imperative APIs that do have mutable state all over the place. But outside of those two areas, what we think has emerged, at least in our experience, is that you should try to keep the rest of your code pure. And basically use referential transparency, take advantage of it as much as possible to manage the complexity of your code. So we just like you to think of these three regions.
And I think and then one way to illustrate this is that these are regions of the stack frame. So when you fire a thread into the JVM, it starts executing methods. Each time a method calls another method, it pushes another frame onto the stack. So this is showing the stack starting at the top and growing downwards. And we've got quite a few methods that called quite a few other methods. I/O should happen at the top. And if anywhere I/O is happening, that's actually the wild region where anything goes. And the top region that's shown orange here may be calling into mutable APIs that are valuable. There's just a ton of value out there in existing libraries that it's really handy to be able to just link and use. And maybe you wrap it and make it more Scala-like, but maybe at least that part is in the wilderness because it's calling into these mutable things. Then at some point you hit pure, and everything in the yellow region on down till you get to purple is referentially transparent. It's actually, you could replace the invocation with the result and it would not change the meaning of your code. Down at the bottom, that's the hot spot. That's actually the part that matters to the performance. So there, a lot of times we switch back to local mutation that's confined to just one thread. The border between the yellow and the purple down here is, there's an immutable object coming back, like make string uses mutation on the inside, but it returns a string, which is immutable. So that from the top, basically as soon as you hit this, it's all referentially transparent on the way down. Any mutation is localized or confined. So Frank is going to give you a specific example.
So how does it work in practice? And we refactor some of our code actually to follow this pattern, and we find it to be really quite useful once you get it. It's sort of really helpful. So in this example, we're trying to generate a PDF document. It's probably a very common task for a lot of enterprise-level applications. And the request to do this comes from the outside, where there is an I/O, and there is a message that you somehow get and receive. And that message handling should be done in the wilderness part of your program. It may also, we don't know how you receive that message, but regardless, whatever API you use there would most likely not follow referential transparency. And you should confine that part of your code very clearly to the wilderness region. However, once you capture this input from the outside world, as you go ahead and transfer that or transform that input into exactly the data that you need for your beautifully formatted PDF document, that code, which is probably the bulk of your application logic code, should really be done in a purely functional way. That's what we think is effective. So again, you would take advantage of referential transparency, which means that you could chain methods together, you can make your code composable, and you should really try to clearly delineate that segment of your code and really adhere to that principle inside that code. However, at the end of the day, you may want to use an existing Java API to create your PDF. Why reinvent the wheel? Such as, let's say, the iText is a very popular Java API. Well, guess what? The iText APIs, for those who have used it, you already know this, it's a super imperative API. It's like baking a cake. You have to do certain things in one step at a time. It does a lot of mutable state on those objects. However, if you confine the use of this API to just one thread, and let's say you return, after you've done with this PDF, you don't do any I/O and you don't do any side effects inside that method. So you definitely don't want to write that PDF to a file inside that method. What you would want to do is return an immutable data structure, such as a vector, a byte, or something like that. And therefore, this confined region appears to be basically fairly functional from the outside world, but inside it could use, in this inside core part, it could actually use whatever it wants, basically, because it's confined.
Right, and that's any of these layers you can call into useful libraries in Scala. That's what's really nice about it, is it allows you to get the benefits of FP, the benefits of OO, and the benefits of all those wonderful, I mean, there's just so much value out there in the world in existing libraries in Java, in JavaScript, or wherever, right?
But one thing I may point out, if you don't mind, is that as soon as you call into an API that does side effects, you're in the wilderness, basically.
Well, no, like this guy,
but the side effect, as long as it's confined.
That's right. So the ones that, like, if they're doing I/O, then definitely you're in the wilderness. Any kind of I/O. But if you can just keep it local to one thread and return something immutable, you're in the confined.
You're in the confined region.
Okay, so just the way we kind of came up with to visualize this architecture, this is kind of like a design pattern, is that if this is your application, all the source code of your application, there's some orange region on the outside, which is the wilderness. That's where the I/O happens. That's where mutation happens because it's useful to call into libraries. On the next in is the pure code, which is hopefully most of the code of your application. And then on the inside, there's that confined region where you have some mutation just for performance usually, that is confined to one thread, and it doesn't have I/O, so that from the outside it appears referentially transparent. So you can basically decide how big or small to make these regions when you define an app, for example.
Yeah.
Yes.
That's right. So you basically could, exactly, I mean, you could shrink or grow one of these regions, but I think the message that we're trying to convey is it's important to really consciously think about this and really make this decision. So it's not the case that anywhere in your code you could just call and do anything pretty much. So, but you should really think of these regions as being separate and distinct in your code base. And we think that this is something that would give you the most benefit, the sweet spot for both O, which you could do in certain regions, as well as FP in your code. So we think that this is kind of a general pattern when you work with the Scala project. It's more like a macro, like a large-scale pattern, programming in the large kind of pattern. And we try to give it a name, but first we thought it's like a bagel because
we like to eat bagels.
Well, we like bagels exactly. Yeah. But then also the problem with the bagel is that the bagel is empty in the inside, whereas this pattern, there's something in the center that's like solid, like something in there.
Well, there's mutation going on.
Mutation going, especially when you eat your bagel, you mutate it. But that didn't really work. So then we thought of the Saturn pattern. It looks a bit like a Saturn, and plus it rhymes. But that also, the problem with the Saturn is that it's even its gases in the inside, but in between the ring, and it's just basically nothing. Whereas here, most of your code is there. So that didn't quite work.
Yeah, so we didn't have a satisfying name for this pattern. And 2 days ago, I was already in Germany, and it actually spoke to me and told me what its name was. And it turns out it spoke German. It said, Bagel? Ich bin kein Bagel. Ich bin kein Saturn, ich bin ein Berliner. Because it looks just like a Berliner, right? So, and it's the jelly-filled donut Berliner, not the American president Berliner. So we think we should call this the Berliner pattern. It is the
it looks like a Berliner.
Idiomatic way to design Scala applications, where you have the outside layer is the wilderness. It has I/O, that's side effects, and it has calls into stuff that's useful in the outside world that may be mutable, and you do it. The cake part is your pure code, and the jelly is the confined region. And there's a lot of mutable goop in there.
Tastes pretty good,
but as long
actually.
as it stays on the inside, from the outside it appears referentially transparent, right? So we wanted to like wrap up by kind of giving you some insight as to, going back to Martin's keynote. He said there's the Haskell on the JVM extreme, there's the better Java extreme, and then there's this third way, which we're trying to like define. Yeah.
So what would Haskell on the VM look like? Well, I think we have some idea. Unfortunately, the jelly part is gone, which we think is kind of tasty sometimes. If you eat too much of it, though, you can kind of go overboard with that. But this is what it would look like. So if you really go and apply those Haskell-like principles to the full extent, then you really don't have any mutable state. You don't have any kind of this confined region doesn't exist.
But you do have I/O.
You have I/O at the end.
This is not just Haskell on the JVM. This is Haskell. Basically, it's pure, but they have to have I/O, and they do it at the edge. And so that's what it is. And as I said, I have seen this work in practice. It works as long as there's a leader on top, right? So what do you think better Java would look like?
Yeah, that's interesting. Well, let's look at it. And this is what it would look like. It's all it's all the GUI stuff. This is like you're basically programming Java in Scala with this pattern. So everything is mutated, everything goes.
And I think that's what it looks like.
That's what it looks like, yeah.
So anyway, Scala we think is this, and it is different than Haskell in that it does let you do mutation, lets you do what you need, right? So it doesn't really, this isn't in the language so much. It's just from experience we think that the most effective way to use Scala is you put your side effects on the I/O to the edge, just like in Haskell, but you also have confined mutations on the inside for speed, which you can't do in Haskell. I mean, and they'll do all kinds of jump through hoops like trampolining to avoid doing a while loop, right? We just do a while loop. But most of it is referentially transparent, so you get the benefit of FP.
Yeah, and if you look at the Scala libraries, a lot of them actually use this pattern already. We just try to sort of like look at it from a bigger perspective. But I think it's already being used in those in that way.
So that's our talk. We just before we go to Q&A, I just want to make a couple things. We did mention that we have an effective Scala workshop that does exist. Our book does not yet, but this does exist. And if you're interested, we could come in and give this. There's the URL.
Yeah, I mean, what I could mention about that is that while we're talking about patterns in the large, we also go into a lot of details in the small.
Right, a lot more detail.
Type classes.
How to use Scala effectively.
We think fun stuff.
Yep. And then Artima is my company, and we are always looking for developers. We do consulting. So if anyone is interested, there's an email address where you can just come talk to me, actually. Also, we are available to do consulting if you need help with Scala. And we are listening. I was honored to be selected as a community representative on the Scala Center Advisory Board, which means I represent you. So I need to hear I need to hear you complain, and oftentimes people don't complain. So if you have any concerns about the direction where Scala is going, please come up and talk to me, or let me know about it, and I can relay that to the Scala Center. So with that, I think we have about 5 minutes for Q&A. Does anybody have a question? There's several questions. Thank you.
So, Bill, what does that remind you of? I mean,
yeah, does anybody know what this is? A diagram of microservice architecture.
That's a heap of Berliners.
Oh, hello?
A heap of Berliners here on the slide.
I think, is his mic on?
Yeah.
Okay. Yeah.
So
It's
first, thanks for the talk. Yeah, very interesting.
Thank you.
And I very much agree with your Berliner pattern. One thing I liked in Haskell is when you are in the wilderness, you also specify this by the type. Haskell has the type I/O, which you may get in some Scala libraries, but in standard Scala, you don't mark that by the type. And this is very helpful to see this in the type when you're doing I/O, and everything else is pure.
Yeah. What he said, just in case you didn't hear him, was that one thing he likes from Haskell is that when you're doing I/O, it is expressed in the type. I agree with that. I think that's very useful. Yeah. Martin, I did hear him one time say that one thing he likes about Haskell that Scala doesn't have is its purity. So I think he has some, like in the back of his mind, some ideas brewing about how to do get more type checking for that kind of thing. But as you're right, today that we don't have that. So it really is wild. That's why we called it the wild region, because anything goes.
Today.
So, yeah, today. Is there another question? Let's see who's gonna. There's one in the back.
Start with this one here. Closer.
Oh, sorry.
One question.
Yes.
A typical thing that you're dealing with in the confined sections are exceptions. Is there a standard approach to avoid leaking exceptions into your pure part of your program?
When you say exceptions, do you mean like throwing exceptions, or do you mean?
Well, you're basically calling Java libraries, and they all throw checked or unchecked exceptions.
Oh.
So let me restate the question for those who didn't hear. But I think if I'm correct, what you said was that in this GUI section, when you call into existing Java APIs, not only you have nulls and whatever in there, but you may those APIs may throw exceptions. And I think the question was what to do about it, like how to handle them.
So basically, at the interface between Scala code and an existing library, I try to Scalify it. So I catch an exception, return an option, or something like that, or catch an exception, return a try, or an either, or something, and try to make it more Scala-like. But that's my code, so that's part of the wilderness, right? On the inside of that, maybe it's better, but it might still be mutable, so even then it would still be part of the wilderness. But what I try to do is try to have most of my code idiomatic Scala and sort of isolate from the libraries I'm using, but sometimes it's just not worth it, and you just call the library. And that's actually part of what Scala is about, is that you can do that. If you need to do it, you need to get something done, you've got a useful library, no matter what its style is, you can just call it.
But confine it to those two regions, that's the important thing.
Yeah.
So like don't mix the two, that's kind of what we're trying to convey.
So there's one in the back here that I think she got a mic. Yeah.
So my question is related to the first one. So I want, it's irritating that it's twice. Yeah. So in your picture, the outside wilderness layer was as big as in the Haskell, or as small. And my question would be, as an opinionated approach, would you recommend using an I/O monad? And do you do that? Or do you just like call your database, get back and give back an either by catching whatever could happen?
Yeah.
Or do you use an I/O and have an interpreter at the very end?
I personally don't use I/O monad. I just do I/O in the outer region, and it's small enough that I can reason about it. But if you want to do I/O, like describe it, basically it's this question. If
you
I
can
go
make
back
it
to
really
the one
thin.
where
this
or this. See how they're two different sizes?
Yeah.
So if you're using I/O monad, it's going to be thinner. If you're just calling this up, maybe it's thicker. It depends on, I mean, how this is. Each project should have an opinion, and that's sort of, you can decide based on the situation what makes sense for your team, and
But I think the important thing is goes back to guideline number 1. Once you decide it, I think it's good to stick with that decision throughout the project, because I have seen projects where things learn differently over time, and that's where a lot of problems can happen, I think.
Okay, thanks.
Sure. Anyone else? We might have time for one more, if you have one. There's one in the middle. In the Mitte. All right.
Do you tolerate logging in the pure section? Because logging is a side effect.
That's good.
So I gave a talk at Northeast Scala Symposium about 6 weeks ago, where I talked about pragmatic purity, about what is actually, that there's certain things we ignore. Like, for example, when you say new, like that new string builder, that was actually a side effect because it mutated the heap, but we don't have to keep track of it because of garbage collection, so we just ignore that, but it's not pure, really. And logging doesn't really change the meaning. So I usually don't think of logging. I think of logging as pragmatically pure. The one thing I would say about it that was said to me after my talk was that if you are doing, like one way to move I/O, like to make this thinner on the outside, is to build up descriptions of side effects that you're going to do, I/O side effects, and then execute them at the end, right? So if you do that, then you usually want the logging to happen when it happens, not when it's described. So you have to be careful that way. But otherwise, I think pretty much that logging is okay to do anywhere because it's actually useful. It's a side effect that helps you.
And also,
about
I don't
your
think
code.
it actually makes your code easier to reason about, not more difficult.
Yeah.
So that probably is.
That's my opinion.
Yeah.
So log away.
logging, even caching, I would say, would be the same.
Yeah,
thing.
caching's another one. It's a side effect that usually you don't have to worry about. It's on the outside, it's referentially transparent. Okay, so I think is lunch next? I don't want to promise lunch if it's not lunch, but anyway,
Yeah, but
thank you very much for your attention, and hopefully it's lunchtime.